Now, each and every term carries important physics, and when you're solving these terms, right, these terms are what give your engineering results. For example, when you solve for shear stress, you're able to calculate your drag coefficient correctly, right? Similarly, if you want to calculate the effect of pressure loss, or if you want to calculate pressure drop accurately, then you need to have the dpdx term, right? Similarly, if you want to get your velocity components correct, you pretty much need all the terms. So let me ask a simple question. Say that you are running an aerodynamic simulation and you want to calculate the drag coefficient. Which term is the most important term? Like, which term should definitely be there in the equation? The answer is you cannot remove any of these terms because this is a coupled system, right? Why is it called a coupled system? Well, if you take a look at your shear stress, that shear stress basically depends on your velocity, right? And your velocity depends on your pressure. Your x component of velocity depends on the other components, and everything is coupled, meaning the only way you can ignore a term is if the effect of the term is small. But if you have to calculate drag coefficient accurately, you cannot ignore any of these terms. So all the terms are important. Just remember that. The reason why people still simplify it, well, if you make your domain in certain way, for example, if you are saying that the flow is two-dimensional, then you can automatically ignore the z terms, correct? Similarly, if your Reynolds number is really, really large, then what happens? Like this, what happens to these terms, right? You can make some approximations there. Similarly, if your pressure drop is very, very small, then you can ignore that. So, but these techniques are done only for analytical calculations. For flow simulations, if you're doing CFD, you should always solve the entire Navier-Stokes equations. If you're just ignoring some terms, your answers will be completely wrong. So like I said, computational testing is all about taking these equations and solving it using a CFD program. Now let me ask another question. This is mainly for people who have used at least one CFD tool so far. So if you have played with ANSYS Fluent, if you have played with ANSYS CFX, Converge, Star CCM, or any other software, CFD software, then you would have definitely seen more equations, right? There are more governing equations in CFD. So with respect to CFD solvers, there are a lot of equations, and especially there is two equations that pretty much everyone remembers. There are two terms. The first term maybe is K, the second term is K epsilon equation or K omega, sure, why not? What is this equation for? I basically said that your Navier-Stokes equation, right, or your continuity, momentum, and energy equation is sufficient when you're doing CFD simulation. Then why do we need additional equations for turbulence? When I initially started the call, I basically said you have these equations and 1, 2, 3, 4, 5 equations. If you solve them, you should be able to solve your fluid. Then why do we need two other equations for turbulent flows? The actual answer is you can actually do something called as a direct numerical simulation. The name sounds fancy, but it is basically solving the entire Navier-Stokes equation as is. If you do that, then there is no need to have any turbulence model. But the problem is the number of computational cells that you need, a function of Reynolds number to the power 9/4. So this, you can assume that this is roughly Reynolds number to the power 3. So if your Reynolds number is 100, then you need 1 million cells to get all the scales, which is fine, which is something that you can do very easily. But if your Reynolds number is 100,000, right, it's pretty much impossible to do a direct numerical simulation. So in other words, you cannot capture turbulence by directly solving these equations. So what you're doing is you're trying to approximate it. And that is where the turbulence model comes into play.